Hi everyone. As you are probably aware, there's a big shortage of chips at the moment. So I'm really happy to present to you today our work on predictive discarding of wafers, which is a crucial element in the manufacturing of integrated circuits and computer chips. Predictive discarding is a very intuitive term, but for some reason it's not standard practice in many of the manufacturing processes, and we really hope to change that as soon as possible. What we mean with predictive discarding is that we can use the process data, which is so abundant in Industry 4.0, to predict the end product quality of an unfinished item during the manufacturing process. And then if the prediction models state that the end product quality will not be reached, we discard the unfinished item as soon as possible. From a sustainability point of view, we can use this to make sure that we minimize the resource consumption that we would otherwise spend on finishing a product that will not reach the sufficient quality. And with resources, you can think of raw materials and energy, but also time. And especially with the chips, which take up to 14 weeks to produce, and the big shortage of those chips, any time that we can save in the manufacturing process to ensure that we can make good quality chips is extremely valuable. There are many steps involved in manufacturing chips, and for this project we evaluated whether we could implement predictive discarding during the photolithography step, which is required to make the integrated circuits that form the heart of the chip. To explain the data that we used and the phase that we are doing the predictive discarding in, I think it's good to go a little bit into the details of what photolithography does. Basically what we do is we have a layer of semiconductor in which we want to make specific patterns such that the integrated circuit works properly. To do this, we put a little layer of photoresist on it, which is a material that reacts to light. And then if we expose it to specific patterns and we shine UV light through those patterns, the photoresist evaporates, leaving us with a spot in the photoresist for which we can etch out the semiconducting material. In that way, we have the same pattern in the semiconducting material as we had on the photoresist. Then we remove the photoresist and we are left with the semiconducting material. And then if we repeat the process, we can make layers upon layers of these for these integrated circuits. And the product that we have now consists of 22 of these layers of material. And as you can imagine, since those chips are extremely tiny, this alignment of these layers has to be done very precisely. And any misalignment between the layers can have a significant impact on the quality of the chips. And that's what we're going to look at, whether we can predict the end product quality from these misalignments in the third layer, as we can see here. The integrated circuits are made on these discs called wafers. And once the 22 layers are finished, these wafers are cut into little pieces, which are called dies. And these dies then form the heart of the computer chips. But before these dies are processed further, each die undergoes several electrical tests to evaluate whether they perform properly. And one of the most important tests is that of power leakage. Power leakage means that we want to see how much current is going through the system while it's in an off state. And of course, in an electronic component, you want to have zero current going through a system if it's off. And then the criterion for the product quality is how many of those dies on the wafer fail this test. And if the number of dies that fail the test is too large, is above a certain threshold, then we discard all the dies from that wafer. So the entire batch of wafers, of dies, is rejected. Even those dies that do pass the test are rejected because they are deemed too unreliable if too many of their siblings pass that test. Now that we've covered the basics of the manufacturing process, let's take a look at what the methodology we use to evaluate whether we could implement predictive discarding into this manufacturing process. For the data analysis, we had data available for 412 wafers, which each comprise of hundreds of dies. And for those wafers, we had data on the alignment, or better yet, the misalignment of the third layer, which is the most critical layer out of the 22. And what we wanted to see is, can we predict the outcome of the power leakage test results from the alignment of the third layer? Because if we can do that, we can save up till 19 layers of production, which is of course a significant improvement if we don't have to do those. For classification, we simply evaluated whether the number of failing dies would be acceptable or unacceptable. And we used 4 readily available classifiers for that, for which I'm not going to go into the technical details because there are many other classifiers that might also do the trick. Before going to the results, it's good to explain a little bit how we got the results and how we ensured that those were as reliable as possible. So what we did was we first took all the data, then split it up into a training and a test set, and that training data was split up in a cross-validation grid search to ensure that we had found the best possible model parameters. And once we found the best possible models, we used those models to predict the outcomes of the test set that the model hadn't seen before, and it's those test results that I'm going to present after this. Of course, those test results are highly dependent on this first split in training and test set. So to ensure that we looked at how stable the results were and how reliant those were on the first split, we did a Monte Carlo replication. So we did this entire process 10 times for different training and test sets splits. Because we rely on predictive models to decide on whether or not to discard a wafer, there's 2 things that can happen if we discard it. Either we discard a faulty wafer, in which case we save up on resources that we would have otherwise spent on finishing the additional 19 layers, or we can make the incorrect decision to discard a wafer which was at that point still good. If that's the case, then we miss out on revenue because the value of the wafer increases after it's finished, but the amount of missed revenue of course depends on the profit margin that we have on the wafer. Obviously, there's also a possibility that the model says do not discard it and just continue the process, and that's exactly what the current practice is. So nothing would change with respect to the current practice. Here we see the model performance in the 10 test sets in the form of recall and false positive rates. Now the recall, also called the sensitivity, evaluates how many of the faulty wafers are correctly rejected by the model and we could correctly discard. The false positive rate is the amount of discarded wafers which were actually good. So of those wafers that we would discard based on these prediction models, how many of those are actually good wafers? And those lead up to missed revenue, and the recall lead up to the benefits because we save up on resources. If we now combine the recall with the resources that we save for every correct discard, and we combine the false positive rates with the missed revenue for every incorrect discard, we can evaluate whether there are benefits of implementing predictive discarding in this situation. One parameter there is the profit margin, because the higher the profit margin, the more revenue we miss for each false positive. And that's why we give here the benefits of predictive discarding in terms of profit margins, where if the profit margin is 0, as you see here on the x-axis, we have a break-even point in which the value of an item that we finished is the same as the production costs. And for example, if the profit margin is 0.6, then the value of the finished item is 60% higher than the manufacturing costs. So if we then combine those results that we just saw for each of these models, then we see here that certain models have benefits in predictive discarding depending on whether the profit margin is low enough. For very high profit margins, it's very, very important not to make any false positives. But if the profit margin is low, the saved resources are much more important than the missed revenue. The previous results shown here again are based on the idea that we would discard a wafer as soon as the prediction model says that it will not reach the end product quality. But when the false positive rates are very costly and we want to minimize the false positives, we can also look at the wafers for which the model is very certain that they will not reach the end product quality. And if we do that and we look at, for instance, the false positive rates and the recall for the wafers of which the model is 70% or more certain that they will not reach the end product quality, we get different results. You see that the recall is lower, but in general also the false positive rate is lower. Except for the support vector classification, which was never very certain at all about any of its classifications. But if we do that, then we can also see what the value is of predictive discarding in those situations. And then you see a little bit of a different result. You see that if we make sure that the false positive rate is lower, we can have benefits of predictive discarding for longer, even with a higher profit margin. More details on the results that I just showed you can find in the proceedings of this conference. But of course, we are already looking forward to see what else we can do with predictive discarding. And one of the things that we want to do is make us do a sensitivity analysis to evaluate what kind of model performances you would need in which situations to obtain benefits of predictive discarding in a manufacturing process. And also now we've looked at classifiers to just classify whether a wafer would be sufficient or insufficient. But we also want to extend that methodology to include online models in which we continuously update the predictions of our quality to, at each point in the manufacturing process, be able to predict whether it will reach the end product quality and decide then whether or not to discard it. And this continuous measuring of product quality is a thing that's already very common in the process industry with their multivariate statistical process control. And it's something that we can learn a lot from also in the manufacturing industry. I'd like to end this talk with a little note on the value of industrial data, because there's so much value in that data, we just have to get it out. And even in historical data, which is usually just stored for reference purposes somewhere at a later point, much of that data is currently unused, and that's kind of a shame. Because if we have so many measurements, if we are able to extract the relevant information out of that, and that can lead to a certain action, like predictively discarding something, then those measurements increase tremendously in value. And especially because we have so much data now in the Industry 4.0, we should really ensure that we get the most value out of that industrial data. And with that, I'd like to thank everyone for listening. If there's any questions or remarks, please feel free to reach out. I'm always open to have nice, lively discussions and get feedback. And I really hope that you will all try to implement predictive discarding in your manufacturing process to ensure that we together work towards a sustainable industry. And I hope everyone stays safe, and we'll meet each other at some point somewhere.